So for today's lecture, what we'll be talking about is the Gaussian elimination. Okay, so this is section 1.2, Gaussian elimination. This is a method in solving linear system. Okay, so in the previous example, we saw this matrix. Okay, from the augmented matrix that we had, we applied some elementary row operations, and then we came up with this matrix. So as I mentioned in that lecture, this matrix is special to us. It has a special name. We call this a reduced row echelon form matrix. Okay, so reduced row echelon form matrix. So what is this reduced row echelon form? Okay, a matrix is said to be in row echelon form if the following properties are satisfied. Okay, so first, if a row does not consist entirely of zeros, then the first non-zero number in that row is 1. We call this the leading one. Okay, so for example, in this matrix, this row here, it does not consist of entirely zeros. The first number in the row, which is this guy, is 1. The first non-zero number. This guy here, the third row, again, this does not consist entirely of zeros. This is 0, this is 0, this is the first non-zero number, and it is equal to 1. Okay? So if a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. We call that a leading one. Next, if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Okay? In this example, we don't have an entirely zero row. So I cannot, for now, I cannot give you that illustration for the second item. Okay? But we will see later. For the third one, in any two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row. So again, in any two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row. Let's look at the example again. This row here, okay, a non-zero row. This is also a non-zero row. So first row, second row. It says that the leading one in the lower row, okay, the leading one in the lower row, in these two guys here, this is the leading one. This is your lower row, correct? Lower row. The leading one occurs farther to the right than the leading one in the higher row. This is the leading one in the higher row. Okay? And notice that for the lower row, it's on the right. The leading one is on the right of the leading one in the higher row. Okay? Okay? Now, let us now consider these two guys. For example, let's consider these two rows here. The second row and the third row. The leading one in the third row is this. The leading one in the second row is this. Third row is a lower row. The leading one occurs farther to the right of the leading one of the higher row. Okay? So far, so good. So that's our third condition. In any two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row. So these three conditions, if they are satisfied, we say that the matrix is in row echelon form. Okay? Okay? And then, if we add the following condition here, furthermore, if the fourth property below is satisfied, we say that the matrix is in reduced row echelon form. Each column that contains a leading one, okay, each column that contains a leading one has zeros everywhere else in that column. Let us go back to this. So this is a column and this is a leading one. Okay? This is a leading one. The other entries in the same column must be zero. So fourth condition is satisfied. If we look at this column here, we said this is a leading one. And all the other entries in that same column, okay, are zeros. Another column here, this is a leading one. And all the other entries in that same column are zeros. Okay? Which means that this matrix here is actually in reduced row echelon form, like what I mentioned here, reduced row echelon form. So let us look at some more examples. In here, these are all in reduced row echelon form. Look at this. This was our previous example, okay, that we said a reduced row echelon form matrix or in reduced row echelon form matrix. This is another example here. This consists or this does not consist entirely of zeros. This is the first non-zero number and it's a 1. We're good. The second row does not consist entirely of zeros. We have here 0, 0, 0, and then the first non-zero number, it's also a 1. So we're still good, at least for the row echelon form. Third row and fourth row, they are rows consisting entirely of zeros. So we put them at the bottom of the matrix. This is the second condition in here. Okay? If there are any zero rows that consist entirely of zeros, or if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. So they are grouped together at the bottom of the matrix. This is a leading one. The first row here, this is your leading one. Okay? And then on the second row, this is your leading one. So the leading one on the lower row is farther to the right than the leading one on the higher row. In fact, it skipped a column. So leading one here, it's on the second column, while the leading one here, it's on the fourth column. Okay? Now, These are reduced row echelon form. So let's check if it's true. We check column wise. This is a leading one. We look at the column of that leading one. This is 0, this is 0, this is 0. So all other entries in the same column of this leading one are zeros. We look at this because this is a leading one. We look at the column, and all other entries in the same column as this guy are all zeros. So condition number 4 is satisfied. And indeed, this guy here, it's a reduced row echelon form. Okay? Questions so far? Now, these are examples where they are in row echelon form, but not in reduced row echelon form. So they are row echelon form, meaning the first three conditions are satisfied. Okay? But that the fourth condition is not satisfied. For example, this guy here, okay, this is a non-zero row. This is the first non-zero entry, it's 1. So this guy here, it's 1. Okay? This is also a non-zero row. Okay? The second row here, it's a non-zero row. The first non-zero entry here, it's 1. On the third row, non-zero row, the first non-zero entry is also 1. If we look at the first and the second row, okay, the leading one on the second row is to the right of the leading one of the first row. If we look at the third row and the second row, the leading one of the third row is to the right of the leading one of the second row. So the first three conditions are satisfied. But the fourth condition, well, if we look at this row here, or this column here, this is a leading one. The other entries in the same column, they are all 0, which is fine for the fourth condition. But if we look at this column, because this is a leading one, so we consider its column. This guy here, this is non-zero. And that is enough to say that this is not in reduced row echelon form, because there is a non-zero in the same column of the leading one. Okay? Of course, you can also talk about the third column here. Okay? For the third column, because this is a leading one here, but there's a non-zero entry here. Okay? So this guy here, it's not in reduced row echelon form, although it is in row echelon form. Okay? For this example, where are the leading ones? This is a leading one. So non-zero row. Okay? The first non-zero entry, it's a 1. The second row, okay? The first non-zero entry is a 1, it's here. The third row, we have here the first non-zero entry. The fourth row, this is the first non-zero entry. So these are all the leading ones. Okay? We look at now the column for the leading ones. So we have this column. This is the leading one, and we have this column. All the other entries are zeros. For this leading one here, we look at this column, but notice you have a -4 in here. And because of that, this is no longer in reduced row echelon form. Okay? If you check the third condition, okay, if you check the third condition, second row here, the leading one is to the right of the leading one of the first row. For the third row here, the leading one is to the right of the leading one of the second row. For the fourth row here, the leading one is to the right of the leading one of the third row. So it means conditions 1, 2, 3 here are satisfied, but condition 4 is not satisfied. Okay? So is it clear? Is the difference between row echelon form and reduced row echelon form clear? Okay, so let's go to our next example here. In each part, suppose that the augmented matrix for a linear system in the unknowns x, y, z has been reduced by elementary row operations to the given reduced row echelon form. Solve the system. So it says we have a linear system in the variables x, y, and z, and the augmented matrix of that linear system was reduced to this. So this is your x column, your y column, your z column. Okay? So what does this mean? In the first row here, it means you have the equation x minus z equals 0 because the y part there, it's 0. For the second row here, x is 0, you have here y plus 2z. This is equal to 1. Okay? And then the third row, it's a 0 row. So it's just 0 equals 0. So we can throw that. But for emphasis, I'll just write 0 equals 0. So 0x times 0y times 0z, that's equal to 0. So how do we solve this system now? So this means that if your z is equal to t, any number, so t any real number, where t is any number, then we have x equals t. You put this on that side, that's x equals t. And then you have y equals minus 2z, so that becomes minus 2t plus 1. And of course, your z is equal to t, according to this. So this guy here is the solution to the linear system that this reduced row echelon form represents. And we call this the general solution. Okay? Next problem here. Still, we have a linear system in the variables x, y, z. And then it was the augmented matrix corresponding to that linear system was reduced to this. And of course, this is still the column for x, column for y, column for z. Take note, this is in reduced row echelon form because the second row and the third row, they are zero rows. So they are grouped at the bottom. And only the first row has non-zero entries. But if we translate this to an equation, this means that we have x plus y plus 2z equals 3. So we are only given one equation. So how do we solve the system? Okay, so if say y equals t, z equals s, where t and s are arbitrary numbers, then you have your x equals. You put this y and z to the other side of the equation, but y is t, so we have minus t. Z is s minus 2s, and then you have the plus 3. And then for completion, let's just write here y equals t, z equals s. So this guy here is the general solution for the linear system that is represented by this augmented or reduced row echelon form. Okay? Another example here. So suppose we have this. Okay? We will see still this is your x column, this is your y column, your z column. This is in reduced row echelon form. This is a leading one for the first row. This is a leading one for the second row. And the leading one of the second row is to the right of the leading one of the first row. This is a leading one on the third row. And the leading one on the third row is farther to the right of the leading one of the second row. So let me just encircle those leading ones. Now, column for the leading ones. The other entries in the same column of the leading ones are all zeros. So this is 0 and 0. For this column, you have here 0 and 0. And for this column, you have here 0 and 0. So indeed, this is in reduced row echelon form. Okay? But how do we solve the system? So again, the first row gives us the equation x minus z equals 0. The second row gives us y equals 0. And the third row gives us 0 equals 1. Notice, this guy here, 0 equals 1, this will never happen. This is a contradiction. So what does this mean? The linear system whose augmented matrix can be reduced into this has no solution. Okay? The linear system has no solution. Okay? Questions? Let us look at the next now. So again, we look at this. We have this example. We also have this example and this example. So in this set of examples, what we actually did was to convert a reduced row echelon form to equations. And therefore, um, the reduced row echelon form helps us solve directly the solution to the linear system. Okay? So how does that one help us? Well, if you have a linear system, okay, if you have a linear system, you can solve that using the methods that we discussed in the first um, lecture, or you can solve that using augmented matrix or through the augmented matrix. And we get the reduced row echelon form of the augmented matrix, okay? And then using the examples here, okay, following the examples that we did here, we can get the general solution of the linear system. Okay, I hope that was clear. So, since we are talking about solutions, let us formalize. If a linear system has infinitely many solutions, then a set of parametric equations from which all solutions can be obtained by assigning numerical values to the parameters is called general solution of the system. Okay, so I already mentioned earlier that this guy here, this is the general solution of the linear system this represents. This augmented matrix represents, or this um, reduced row echelon form of the augmented matrix represents. Similarly, this guy here. This is a general solution or the general solution. Okay? And you call this t here parameters. And look at that, where t is any number. It means that if you change your t with an actual number, there will be values for x, y, z. And those values, okay, will give a solution to the linear system. Okay? In this example, you have two parameters, t and s. So if you choose a specific number for t and a specific number for s, if you substitute them in this to these equations here, then you will get an actual solution to the linear system. Okay? So general solution. Okay? So now, how do we solve the linear system using the augmented matrix? We mentioned that we can reduce it to its reduced row echelon form. And once we have the reduced row echelon form, we bring back the equations to solve for the general solution or actual solution if there's only one solution. Okay? So our goal is to solve the linear system. And how do we do that? I already mentioned the term elimination method. So we are eliminating variables. Okay? If we look at this, if we look at these examples here, say this, what we actually did on the third row was to eliminate the z. And therefore, the first and the second row only has xz or yz. On the first row here, we eliminated the y. That's why on the first equation, we just have x and z. On the second row here, we eliminated the x. That's why we only have y and z. On the third row, we eliminated all the variables because that was possible for us. And therefore, we have this general solution. For this, we have this general solution. Okay? On the second and third rows, we have eliminated all the variables. And we were able to get 0 equals 0 on both second and third rows. On the first row, well, we were not able to eliminate the variables or any of the variables. Okay? But it's fine because we only have this one equation, which means that we can just write one of the variables in terms of the other two variables, just like what we did in here. From here, we can write x in terms of y and z. Okay? And then we replace y and z with the parameters t and s to get this general solution. Okay? Also in here, on the first equation here, or on the first row here, we were able to eliminate y. On the second row here, we were able to eliminate 0 and z. On the third row here, we were able to eliminate x, y, and z. However, the constant part, or the right-hand side of the third row, it was not 0. And therefore, we have this 0 equals 1, which is a contradiction. And that's why we conclude that this system has no solution. That is elimination method. Okay? But let us enumerate the steps of this elimination method. First, we locate the leftmost column that does not consist entirely of zeros. Choose one entry if there are many. So suppose you have a linear system. So suppose you have a linear system, you write the augmented matrix. Okay? You write the augmented matrix. So let us borrow again this example. We have this linear system. We have the augmented matrix here. So first step, locate the leftmost column that does not consist entirely of zeros. Choose one entry if there are many. In here, this is this row, okay? The leftmost non-zero entry, it's on the first column. Same is true with the second and the third row. So there are three choices. Then we just choose one of them. Okay? So choose one entry if there are many. Then we can choose the first row. We can choose the first row. We can choose now this entry here. Okay? Second step. Interchange the top row with another row, if necessary, to bring a non-zero entry to the top of the column found in step 1. So, what does this mean? In this guy, we already chose this entry, and it's already on the top row. Okay? So, we don't have to do any interchanging of rows. Suppose we chose third row here. Of course, the leftmost non-zero entry is also on the first column. So we can choose this. If we chose this third row, then the second step tells us that we interchange this row with the topmost. Okay? We will interchange this with this. And do you still remember your your elementary row operations? That's a valid operation. interchange two rows, and it won't change the solution set of the linear system. So you can do that. Okay? So if you chose the third row, you put the third row to the top row. Okay? But again, in our example, we initially chose the first row. So we will not do any interchanging of rows. That's our second step. Third step, if the entry that is now at the top of the column found in step 1 is not equal to 1, multiply the first row by its reciprocal in order to introduce a leading one. In this example, it's already 1. Okay? It's already 1. So we don't have to do any multiplication. But suppose we did choose the third row here. So from here, we do interchanging. So row 3 interchange with row 1. We will end up with something like this. 3, -7, 4, 10. And then -1, 1, 2, -1, -2. Sorry, -1, -2, 3, 1. And then we have 1, 1, 2, 8. So this was step 2. If we chose the third row as in the step 1. Step 2, we interchange. Step 3, because this guy here, it's not equal to 1, we multiply this row by the reciprocal of this guy here. So what does this mean? That step 3 means we multiply the first row by 1/3. The reciprocal of this entry to introduce the leading one. So notice, if we do that, we will now have 1 there. Okay? So multiply the first row by 1/3. We will now have 1 here. And then we will have 7/3. And then 4/3. And then 10/3. And then we did not do anything with the second row and the third row. So we'll just copy it. -1, -2, 3, 1. And then 1, 1, 2, 8. So this is your step 3. You want to introduce the leading one. Okay? For this, we did not do that because, well, we chose the top row already. It's already on the top row. We do not do the interchange because we use the top row. We do not do multiplication because this is already a leading one. So we can skip those first 3 steps. Okay? So far, so good. So again, this bottom here, this is just to illustrate the steps that we are using. Okay? Step 4. Add a suitable multiples of the top row to the rows below so that all entries below the leading one becomes 0. So what does this mean? This is already a leading one. This guy here is a leading one. Okay? You need to add something, okay, to this first row from the second row or the third row so that this guy here, this -1, will become 0. And this +1 will become 0. Okay? So you will replace this second row by adding something, okay? By adding something to this second row using the first row, that will make this entry here 0. Similarly, you will replace this third row by adding something to the third row using the first row, so that this entry here becomes 0. For instance, we can replace the second row by adding second row plus first row. The third row, we can replace the third row by adding the third row minus the first row. So why did we choose this? For this guy here, negative 1 plus 1, that will become 0. So let's just write this. So 1, negative 7 over 3, 4 over 3, 10 over 3. So if we do this, what will happen to the entry here? So negative 1 plus 1, this will become 0. And then you compute negative 2 plus negative 7 thirds, you put it here. 3 plus 4 thirds, you put it here. 1 plus 10 thirds, you put it here. For the third row, we have here 1 minus 1, and that becomes 0. Correct? So 1 minus 1, that becomes 0. And then here you have 1 minus negative 7 thirds. You put it here. Similarly for the other entries. You just follow this elementary row operation that you are using. So far, so good. Okay? And notice, this is a leading one, and then all the entries on the column of the leading one are now zeros. So what we are actually doing is trying to reduce the augmented matrix to its reduced row echelon form. So that's step number 4. Add suitable multiples of top row to the rows below so that all entries below the leading one becomes 0. Step 5. After doing all these guys here in step 4, what you're going to do is to move down. So, cover the top row in the matrix. Okay? Cover the top row in the matrix. And begin with step 1 again. Applied to the submatrix that remains in the after step 4. So what is that? So before I erase these guys here, is step 1 until step 3 cool? Ah, step 1 until step 4. So let me erase this part. Let me now use this guy here. Let me now use this guy here. So step 1, we choose this row here and this entry here. Step 2, we don't have to interchange, so it's fine. We can skip step 2. Step 3, we can also skip that because this is already a leading one. Okay? Let us do step 4 from here. So from here, let me just put it this way. Step 4, it's row 2. So we will replace row 2 by row 2 plus row 1. We will replace row 3 by row 3 minus 3 row 1. So what will happen to the matrix? We are not changing row 1, so we'll just copy it. 1, 1, 2, 8. And then row 2 becomes row 2 plus row 1. So this guy here, minus 1 plus 1, that's 0. Minus 2 plus 1, that's minus 1. 3 plus 2, that's 5. 1 plus 8, that's 9. Third row, we do third row minus 3 times row 1. So 3 minus 3 times 1, that will become 0. Minus 7 minus 3 times 1, that's minus 10. 4 minus 3 times 2, that's minus 2. 10 minus 3 times 8, so 10 minus 24, that's minus 14. So after applying these elementary row operations here to this matrix, we will end up with this. This is our leading one, and all the entries in the same column of that leading one, here is 0 and here is 0. So we're done with step 4. So what is step 5? You cover the first row, and then you just look at this matrix. So meaning you apply steps 1 to 4 again to the submatrix here. So meaning on these steps here, we will no longer touch, at least for now, we will not touch row 1. So row 1 will remain as 1, 1, 2, 8 until we need it again. So look at rows 2 and 3 only. What is step 1? Choose the leftmost, non-zero. The leftmost non-zero in row 2, it's in column 2. The leftmost non-zero in row 3, it's also in column 2. So you can choose any. But let's just choose this row 2. Okay? So keep in mind, we are no longer touching the first row, meaning we are just working on this submatrix. So in this submatrix, the second row is actually the top row. Correct? The second row is actually the top row. So we chose this entry here. It's already on the top row for this submatrix. So we can skip step 2 again. Okay? What about step 3? The entry is -1. It's not +1. So we have to make this a +1 by multiplying -1. So if we multiply -1 to that second row, we will end up with 0. And then that's because 0 times -1, that's 0. -1 times -1, that becomes +1. Okay? And then -1 times 5, that's -5. -1 times 9, that's -9. And then we did not do anything to the third row, so we'll just copy it. 0, -10, -2, negative 14. So we are on step 3 for this submatrix. So again, just for emphasis, I'll just write this, okay? But in actual solution, you don't have to write this. But track, keep tracking the submatrix you are working on. So step 3, this guy. What is step 4? You have to make all the other entries in the same column of the leading one zeros. So this guy here becomes a leading one. Okay? So we want to make this here, this entry here, 0. And to do that, well, we can just add third row plus 10 times the second row. So if we do that, first row, you did not change it. So it's 1, 1, 2, 8. Second row, you do not change it. We're just using it. So this is still 0, 1, negative 5, negative 9. For the third row, you do this. Third row plus 10 times the second row. So 0 times, 0 plus 0, that's still 0. Negative 10 plus 10 times 1, that will become 0. Negative 2 times 10, negative 2 plus 10 times negative 5, that's negative 52. And then negative 14 plus 10 times negative 9, that's negative 104. Okay? So this is a leading one, and all the entries below that leading one are already 0. So this is your leading one, and all the entries below it are 0. And then that's your step 4. You go again to step 5. You cover the top row. So this time, you are covering this row here, and you are covering the second row also. So you're just gonna work on the third row. Okay? But since you're only working on a single row, then your step 1, you are forced to use that row 3. So again, this time you're just working on this submatrix. So you are forced to use this row here. This is a non-zero entry. We want that to be a leading one. So what you can do is, well, to multiply negative 1 over 52 times the row 3. So the reciprocal of this guy here, reciprocal of negative 52, it's negative 1 over 52. Okay? So far, so good. And then you continue. You continue until you have presented all the leading ones. Okay? So let's continue on this side here. Let's continue on this side here. So we had negative 100, so negative 1 over 52 of row 3. Our first row, it's 1, 1, 2, 8. So 1, 1, 2, 8. Our second row, it's 0, 1, negative 5, negative 9. Correct? And then our third row, it's 0, 0, negative 52, negative 104. But we are dividing by negative 52. So this becomes 0, 0, 1, 2. Okay? So the third row is being multiplied to negative 1 over 52. Or your third row is being divided by negative 52. So negative 52 divided by negative 52, that's 1. Okay, that's 1 here. And then negative 104 divided by negative 52, that's 2. That's why you have 2 here. Okay? And now, since you're already on the last row, you cannot go down further. So you are done with step 5. Continue the process until the entire matrix is in row echelon form. This is in row echelon form. This is a leading 1. So this is a leading 1, leading 1, leading 1. The leading 1 on the lower row, for example, the leading 1 on the second row is to the right of the leading 1 of the first row. The leading 1 on the third row is to the right of the leading 1 of the second row. So there are no 0 rows here. So we don't have that second criterion. So continue the process until the entire matrix is in row echelon form. Now, let's look at step 6. Look at this, step 6. Beginning with the last non-zero row and working upwards. Okay? Add suitable multiples of each row to the rows above to introduce 0 above the leading ones. So what does that mean? Beginning on the last row, okay, you move upwards. The last row, we have this leading one here. We want to introduce zeros to all the entries above it. We want to make this 0. We want to make this 0. Okay? And to do that, we will use the third row. So, we will replace now the second row by adding second row plus 5 times the third row. So we are using the third row. We are replacing the second row. So the third row remains the same. You have 0, 0, 1, 2. The second row will be replaced by this. Second row plus 5 times the third row. So here 0 plus 0, that's still 0. Here 1 plus 0, that's still 1. Here, negative 5 plus 5 times 1. So that becomes negative 5 plus 5. That becomes 0. In here, negative 9 plus 5 times 2. So negative 9 plus 5 times 2, that's negative 9 plus 10. So this is 1. So we were able to replace this with 0. Let's look at this. We want to replace this guy with 0. So again, using the third row, we will replace first row by adding first row minus twice the third row. Okay? So what will happen to that? First row minus twice the third row. 1 minus 0, that's still 1. 1 minus 0 here, that's still 1. Then 2 minus 2 times 1, that becomes 2 minus 2. So this becomes 0. And then 8 minus 2 times 2. So 8 minus 4, that becomes 4. correct? And then there are no more entries above this leading one. So from the last row, we move up. Let's get the row above the last row. So we are now on the second row. This is a leading one. The entry above this leading one, it's non-zero. So we want to change this to 0. So what will we do? We are not going to change the third row. 0, 0, 1, 2. We are also not going to change the second row. 0, 1, 0, 1. But for the first row, we want to change this to 0. And to do that, we will use this second row. So the first row will be replaced by first row minus the second row. So that this will become 0. So 1 minus 0, that's 1. 1 minus 1, that's 0. 0 minus 0, that's still 0. And then 4 minus 1, that becomes 3. And there are no other entries above this guy here. So you move up. But this is already the first row. And therefore, you are done. Look at this. Step 6. From this entry, step 6 allowed us to get a reduced row echelon form. Okay? So beginning with the last non-zero row and working upward, add suitable multiples of each row to the rows above to introduce zeros above the leading ones. Once you finish this step 6, you now have the reduced row echelon form. So steps 1 up to 5, you will get row echelon form. So you will repeat all the process until you have the row echelon form. Step 1, step 2, step 3, step 4, step 5, then go back to step 1, step 2, step 3, step 4, step 5, then go back again if needed until you have row echelon form. When you have the row echelon form, you now go to step 6. Okay? So this is the elimination method. Okay? So let's have some notes here. The step-by-step process or the step-by-step method or algorithm described here, okay, is called Gauss-Jordan elimination. So from steps 1 to 6, Gauss-Jordan elimination. The algorithm has two parts. The forward phase, that's from steps 1 until that's from step 1 to step 5. And then the backward phase, that's your step 6. Obviously, forward phase, because you start from the top row, you go down. On the other hand, your step 6, you start from the bottom, you go up. Okay? So forward phase and backward phase. If you only do the forward phase, if you only do steps 1 to 5, okay, then the method is called Gaussian elimination. Okay? Gaussian elimination. The forward phase produces a row echelon form. So if only steps 1 to 5, you have Gaussian elimination. If you were asked to do or to use Gauss-Jordan elimination, you have to include step 6. Okay? Questions so far? So we will work on some more examples later. Let's just give some more remarks about this Gauss-Jordan elimination method and the row echelon form and reduced row echelon form. Now, every matrix has a unique reduced row echelon form. There's only one reduced row echelon form for whatever matrix you have. Okay? On the other hand, row echelon forms are not unique. There can be many other row echelon forms depending on the elementary row operations you use. Okay? So there will be several row echelon forms for a matrix, but there will be only one reduced row echelon form. So most of the time, I will be asking you for the reduced row echelon form so that we will have the same answers. Okay? Now, although the row echelon forms are not unique, the reduced row echelon form and all row echelon forms of a matrix M have the same number of 0 rows. Okay? And the leading ones always occur in the same position. Okay? So for example, say this is in this is in row echelon form. Okay? This is in reduced row echelon form. There are no 0 rows here, so we'll not talk about that. But let's have the leading ones. This leading one, the location of the leading one here, this is also a leading one here. The location of the leading one here, the same as this. The location of the leading one here on the second row is also on the same location of the leading one. The leading one on the third row has the same location as the leading one here. Look at this. This is still in row echelon form. This guy here is in row echelon form. And the leading ones, here, 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 they are the same locations. Or they are in the same location as in this row echelon form or this reduced row echelon form. These two guys, row echelon forms. Both of them are row echelon forms. They came from the same matrix. You have two row echelon forms. This guy, it's reduced row echelon form, okay? And there are no other reduced row echelon form for the original matrix here, for the augmented matrix of this linear system. Okay? So that's what it meant for this statement. The leading ones always occur in the same positions. And there is a name for that. We call them pivot positions of M. Okay? So the pivot positions, those are the location of, or the locations of the leading ones. And of course, a column that contains a pivot position is called a pivot column. Okay? So these are all pivot positions, these guys here. Okay? This is a pivot position, this also is a pivot position, and this also. This guy here is a pivot column. This guy here, it's a pivot column. This guy here, it's also a pivot column. Okay? If we look at the other examples from before, let's have it here. This guy, this guy, this guy, and this guy, they are all pivot positions. So this, 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 this. This is a pivot column. This is a pivot column. This is a pivot column. This is also a pivot column. For this example here, this is a pivot position. This is also a pivot position. This is a pivot column. This is a pivot column. Are we clear? Now, there's a possibility that you will see this kind of matrix. Say 0, 1, 1, 0, 3, 0, 0, 0, 1, 1, and then 0, 0, 0, 0, 1. Let's make this 0 also. So for this matrix, this is a pivot position because this is a leading one. This is also a pivot position because this is a leading one. This guy here, look at this. For this leading one, all the other entries in the same column, so this is your pivot column, all the other entries are zeros. This guy here, this is 1. And all the other entries with the same column as this are zeros. But this is not a pivot column. This is not a pivot position because this is not a leading one. Okay? However, this guy here, this is a leading one, and therefore it's a pivot position, and this guy here, it's a pivot column. Okay? Questions? Some more remarks and facts. If a homogeneous linear system has n unknowns, and if the reduced row echelon form of its augmented matrix has R non-zero rows, then the system has n minus R free variables. Okay? Example. Let us look at that matrix from the previous example. So it has, you have here, let us remove the first column. So we have 1, 4, 0, 3. And then here 0, 0, 1, 1. And then 0, 0, 0, 0. Okay? So we have here, say, this is your x sub 1, x sub 2, x sub 3, x sub 4. You have 4 variables. Okay? You have 4 variables. The augmented matrix has R non-zero rows. What are the non-zero rows? These two guys. The third row, it's a 0 row. Okay? So in here, you have 2 non-zero rows. Okay? Then the system has n minus r variables. So you have 4 variables. Sorry, then the system has n minus r free variables. You have 4 variables, 2 non-zero rows. This implies that we have 4 minus 2 free variables. So what are these free variables? These variables will take the parameters. Okay? Let us try to understand this. We can write this in equation form. We have x1 minus 4x2 plus 3x4 equals 0. Take note, homogeneous linear system. So this is the coefficient matrix of your system. Okay? And then for the second row here, you have x3 plus x4. This is equal to 0. Okay? So notice, your x1, your first equation has the variables x1, x2, and x4. So we can write x1 in terms of x2 and x4. You will have x1 equals 4x2 minus 3x4. For the second equation, you have x3 and x4. We can write x3 in terms of x4. So x3 equals negative x4. So this guy here, x sub 2 and x sub 4, these are your free variables. So 2 free variables. Okay? 2 free variables. You have the reduced row echelon form. You have 4 variables. You have 2 non-zero rows. Okay? So 4 minus 2 free variables. 2 free variables. Let's have another example. Suppose you have the reduced row echelon form of the augmented matrix. It's 1, 1, 2, 3. And then here 0, 0, 0, 0, 0, 0, 0, 0. Homogeneous, take note again, homogeneous. So you will have here 4 variables, x4, x1, x2, x3, x4. Okay? If you look at this reduced row echelon form, this is 0 row, this is 0 row. We only have 1 non-zero row. So here, 1 non-zero row. And we have 4 variables, x1 until x4. We have 4 variables. So according to this theorem, we should have 4 minus 1 free variables. Correct? So 3 free variables. If we convert this to equation, okay, we have x1 plus x2 plus 2x3 plus 3x4. This is equal to 0. We just have one equation because this guy, it's just 0. This guy, it's just 0. We can write x1 in terms of the other variables. So x1 equals negative x2 minus 2, x3 minus 3x4. So this guy here, and guy here, these are your free variables. So 3 free variables. Understood? So again, this is only for the homogeneous linear system. Okay? Questions so far? Next, a homogeneous linear system with more unknowns than equations has infinitely many solutions. There are more unknowns than equations, okay? Then also homogeneous linear system, then it will have infinitely many solutions. Okay? If you have free variables, then the free variables can take any number. So you will have infinitely many choices, and therefore you have infinitely many solutions. Okay? Questions? So, for the remaining of the session, we'll just do examples. So, and these are the examples that we will work on. Okay? So, for the remaining session, I will work on this problem on the record and also this problem here on the record. Okay? For the other problems, I will um, answer them. I will give the solutions, but they will not be included in the recording. Okay? Now, if we look at these last two examples here, notice you have y squared, z squared. Here you also have those squares. So if you observe this, you have solved the following systems. I did not say that the system is linear. I just said solve the following systems. So you might ask, sir, we are only talking about linear systems. So why now that we have nonlinear here? We will see later that these two examples, we can actually convert them to a linear system. So we will solve these two guys using the methods that we know when solving linear systems. Okay? So let's work on our first example here. Solve the linear system using Gaussian elimination. Okay? Actually, we will continue with the Gauss-Jordan, meaning we will continue with step 6, not just the Gaussian elimination, not just the steps 1 to 5. So, let's start with the solution. First, we write the augmented matrix for this linear system. So there is no x here, meaning it must be 0. Then here you have negative 2, then 3, and then 1. Here you have 3, 6, negative 3, negative 2. And then here we have 6, 6, 3, 5. So keep in mind, this is your x, this is your y, and this is your z columns. This guy here, that's your right-hand side. So I think I mentioned that sometimes I write this division. I mean divider. So this is the matrix of coefficients. This is the right-hand side or the column of constants. Okay? So, let's do Gaussian elimination now. Here, this is the leftmost entry. It's equal to 0. So, on the first column, that's the leftmost column. This is 0, this is 3, this is 6. So only second row and third row have non-zero leftmost entry, which means we have to choose either second row or third row and put it on the first row. So here's what we're gonna do. We choose the second row, and then we interchange it with the first row. So second row, interchange it with the first row. So what will happen? The second row here becomes our first row. So you have 3, 6, -3, and then -2. The first row becomes the second row. So we have 0, -2, 3, 1. We did not do anything on the third row, so we'll just copy it. 6, 6, 3, 5. So this is first and second step. First step, we chose second row. Second step, we interchange. Third step, we want to make this a leading one, which means we have to divide the first row by 3. So we have 1/3 of the first row. What will now happen to the matrix? So we'll just divide the first row by 3. So 3 divided by 3, that's 1. 6 divided by 3, that's 2. -3 divided by 3, that's -1. Then -2/3 divided by, -2 divided by 3, that's -2/3. And then we did not do anything on the second and the third row, so we'll just copy them. 0, -2, 3, 1. Then here we have 6, 6, 3, 5. That's step 3. Step 4, we now have a leading one here. We want to make all the entries below this leading one zeros. This is already 0. So we'll just replace now the third row. And to do that, we apply elementary row operations. We'll now change row 3 by row 3 minus 6 times row 1. Okay? So row 3 minus 6 times row 1. Okay? So if we now do this operation, we are not doing anything on row 1, so we'll just copy that. So 1, 2, -1, -2/3. We are also not doing anything on row 2, so we'll just copy 0, -2, 3, 1. For the third row, we have 6 minus 6 times 1. That becomes 0. And then here you have 6 minus 6 times 2. That becomes 6 minus 12. So this becomes -6. Here you have 3 times, 3 minus 6 times -1. That becomes 3 plus 6. So that's 9. And then here you have 5 minus 6 times negative 2/3. So 6 times 2/3, that is what? 4. So you have 5 plus 4. That becomes 9. So try to check the arithmetic there. And then now here, you see, this is the leading one. All the entries below this leading one are all 0. So we can now go to step 5. We cover this guy here and then work on the submatrix. So we work on this. We now start working on this submatrix. So we do again steps 1 up to 4. Okay? Now, we have, so let's copy row 1. It's 1, 2, negative 1, negative 2/3. And then what we're going to do is to choose between rows 2 and 3. Okay? This is the leftmost number. This is also this is the leftmost non-zero number. This is also the leftmost non-zero number, and they are on the same column. So we can just choose either 2 and 3. Okay? So let's just choose second row. So we fix the second row in that row. Now we proceed with step number 3 because we don't have to interchange. Step 2 is interchange. Step 3, we want to introduce a leading one, which means if we want this to make if we want to make this 1, we divide the second row by negative 2. So we have negative 1/2 of the second row. So if we do that, what will happen? Of course, 0 divided by 2, that's just 0. And then here you have negative 2 divided by negative 2, that becomes 1. Or negative 1/2 times negative 2, that's 1. Here you have negative 1/2 times 3, that's negative 3/2. Here, negative 1/2 times 1, that's negative 1/2. And then we did not do anything on the third row. So we'll just copy it. 0, negative 6, 9, 9. So this guy here, it's a leading one now. We want to make all the entries below this leading one 0. So we want to convert this to 0. To do that, well, we can add row 3 plus 6 row 2. Correct? So this will become 0 after applying this row operation here. Again, we did not do anything on row 1. So we'll just copy it. 1, 2, negative 1, negative 2/3. We're not going to do anything to row 2. So we'll copy it also. 0, 1, negative 3/2, negative 1/2. For the third row, we apply the operation. So we have 0 plus 0, this is 0, negative 6 plus 6 times 1. So negative 6 plus 6, that is 0. Then 9. plus 6 times 3 halves. So 9 plus 6 times 3 halves. So 6 times 3 halves, that's 9. So 9 minus 9, that is also 0. And then here, 9 plus 6 times negative 1 half. So 9 minus 3. So 6 times 1 half, that's 3. So 9 minus 3, that becomes 6. Okay? Now look at this. Look at this matrix. Okay? Remember, first column is still for the variable x, second column is for y, third column is for z. This guy here, it's your constant column. Okay? If you look at the last row here, so this row here tells you that you have 0x plus 0y plus 0z equals 6. Or you have 0 on the left-hand side, 6 on the right-hand side. And this is a contradiction. 0 equals 6 is never true. So what does this mean? This guy here has no solution. Therefore, the system has no solution. Has no solution. Okay? Okay? Any questions? Let's work on the next example. So for this, look at this. You have x plus y squared plus z equals 6. X minus y squared plus 2z equals negative 2. 2x plus y squared minus z equals 3. So as I have mentioned, this is not a linear system because of this y squared. Okay? Let me check something. Okay, so in this example, I also had z squared. But anyway, let's work on the one without the squared. It doesn't matter. It's still non-linear. This is still non-linear because of the presence of y squared. But I want to work on this. Okay? And I said earlier, this is non-linear, but we can convert this to linear system. Since I have y squared in everything or in every equation, and there's no linear y, I still have three variables. The variables are x, y squared, and z. So if we let, so if we let say y bar equals y squared, or let's say w, let w be equal to y squared, then this system here can be now written as x plus w plus z equals 6, x minus w plus 2z equals minus 2, and then 2x plus w minus z equals 3. And now it looks linear. You don't have that squared. Correct? So we can use our methods in solving linear equations. Linear systems, I mean. So first, augmented matrix. We have 1, 1, 1, 6. And then we have 1, negative 1, 2, negative 2. And then we have 2, 1, negative 1, 3. Keep in mind, this is x, this is w, this is z. This column here, the second column, it's w. And take note, our original variable was y squared or y. But for the moment, let's work on this augmented matrix where the second column is the column of coefficients of w. So let's use Gauss-Jordan elimination. The first column, this is the leftmost entries for each row. And all of them are non-zero. So we can choose this entry here. Okay. We can choose the first row. So we don't have to do step 2, which is interchanging. Also, this is already 1. So we don't have to do step 3. We don't have to divide this row with something because it's already leading 1. So we proceed immediately to step 4. This is a leading 1. We want to make this 0 and this 0. To do that, we can replace row 2 by row 2 minus row 1. And on this step, we will replace row 3 by row 3 minus 2 row 1. Take note that in this combined step, we are only using row 1. And we are not changing row 1. Okay? We are replacing row 2 with another row and row 3 with another row by doing these operations. So we are not changing row 1, we'll just copy 1, 1, 1, 6. For row 2, we have row 2 minus row 1. So 1 minus 1, that's 0. Negative 1 minus 1, that's negative 2. 2 minus 1, that's 1. Negative 2 minus 6, that's negative 8. And then for the third row, we have third row minus 2 row 1. So 2 minus 2 times 1, that's 0. 1 minus 2 times 1, that's negative 1. Negative 1 minus 2 times 1, that's negative 3. 3 minus 2 times 6, that's negative 9. Please check my arithmetic there. Okay. So this is the leading one. All the entries below it are all zeros. So we can now cover this first row. We'll just work on second and third rows. And again, this is just 0. So whatever we do between second and third row, it won't affect these two guys. So it's like you're just working on this submatrix here. So again, for the last time, I'll put this guy here so that I can emphasize that I'm just working on this submatrix, which means that first row, we just copy it for now. 1, 1, 1, 6. Now, between second and third row, what I'm gonna do, instead of choosing row 2 as the top row, we can do that because this leftmost entry here, this leftmost non-zero entry here, it's -2. The leftmost non-zero entry, -1, and they are on the same column. So we can choose between 0 and between row 2 and row 3. But what I'm going to do is to choose row 3 as the top row. It's because for row 3, I don't have to divide uh, with non 1 or -1 number. Okay, to make this clearer, if I use row 2 as the top row, I will have to make this -2 a leading one. If I do that, I will divide the second row by -2. But notice, if I divide by -2, I will have some fraction. You will have 1 divided by -2. And to be honest, working with fractions, it's sometimes not easy. So I want to avoid working with fractions. For the third row, I'll just have to divide by -1 or just multiply by -1. And I won't have any fractions. You get that? So it will be easier if we put this third row to the second row. If we make this row here the top row. So we interchange row 3 and row 2. So the row 3 now becomes row 2. We will have 0, -1, -3, -9. And then row 3 now will be 0, -2, +1, -8. So again, I'm still working on this submatrix. So this is step 1 for this submatrix. Actually, that is step 2. Step 1, I chose row 3. Step 2, I interchanged them so that row 3 becomes the top row of this submatrix. Step 3, I want this to be +1. So I will have to multiply the second row by -1. So if we do this, again, we'll just copy the top row, the first row. We are not doing anything on that. 1, 1, 1, 6. For the second row, we'll just remove those negatives. 0, 1, 3, 9. For the third row, we don't do anything on that, so we'll just copy. 0, -2, 1, -8. Then I want this to be 0. I'll use row 2. So if I do that, what we can do is to add row 3 plus twice row 2. So I'm just using row 2 to replace row 3. Okay? And we will replace row 3 by row 3 plus 2 row 2. So again, we are not doing anything on row 1. We'll just copy 1, 1, 1, 6. Row 2, we are also not doing anything on that for now. So we'll just copy 0, 1, 3, 9. For row 3, we have 0 plus 2 times 0. So again, that's just 0. Negative 2 plus 2 times 1, that's 0. 1 plus 2 times 3, that's 6. So 1 plus 6, that's 7. And then negative 8 plus 2 times 9. 2 times 9, that's 18. Negative 8 plus 18, that's positive 10. Okay? Now, this is the leading one. The entry below it is 0. So we'll just go down and then repeat the process. So we'll just work on the third row. The leading entry, it's 7. So we can divide by 7. So 1 over 7 of row 3. Now we are forced to work with fractions. So we are just dividing row 3 by 1. So let's copy. Sorry, we are dividing row 3 by 7. We're not going to touch rows 1 and 2 for now. We'll just copy them. 1, 1, 1, 6, 0, 1, 3, 9. Then here we have 0, 0, 1, and then 10 over 7. Okay? So this is the last row. Now we proceed to step 6. We now move upwards. This is the leading one. We want to make this 0. Also, this guy here, we want to make this 0. So now, we are going to replace row 2, or let's start with row 1. We are going to place row 1 by row 1 minus row 3. Okay? Let me write the matrix here. So we are not changing row 3, so we'll just copy it. 0, 0, 1, 10 over 7. Okay? Row 1 becomes row 1 minus row 3. So you have 1 minus 0, that's still 1. 1 minus 0, that's still 1. 1 minus 1, that becomes 0. And then 6 minus 10 over 7. So this is where the um, the difficulty, quote unquote, will arise. So we'll have 6 minus 10 over 7. So this guy here, it's over 7, and you have 42 minus 10. So it's 32 over 7. So 32 over 7. So that's for row 1. For row 2, we want to make this entry here 0. So we replace row 2 by row 2 minus 3 row 3. So row 2 minus 3 row 3. So 0 minus 0, that's still 0. 1 minus 0, that's still 1. 3 minus 3 times 1, that becomes 0. And then for this, you have 9 minus 3 times 10 over 7. Let's write the scratch part here. 10, 9 minus 3 times row 3. So that's 30 over 7. So this is equal to, denominator is 7. 9 times 7, that's 63 minus 30. So that's 33 over 7. Okay? So for this leading one, all the entries above it are all 0. We now move to the higher row, row 2. This is a leading one. The entry above it is still 1. So we have to change row 1 again, but we'll just have 1 or row 1 minus row 2. So if we do this, we have 1 minus 0, that's still 1. 1 minus 1, that will become 0. 0 minus 0, that will become, well, that is still 0. 32 over 7 minus 33 over 7, that's negative 1 over 7. And then row 2, we did not change it. Also row 3, so we'll just copy them. So 0, 1, 0, 33 divided by 7, and then 0, 0, 1, 10 over 7. Okay? Okay. So from here, take note, this is for the variable x, for the variable w, for the variable z. So what does this mean? If we convert this to equations, we have x equals negative 1 over 7, w equals 33 over 7, and z equals 10 over 7. Okay? You got these three values. Keep in mind, keep in mind, you have w equals y squared. So you have to bring back the original variable y. Okay? So from here, it means that, let me just write it here. I got w equals 33 over 7, but originally w was y squared, which means that y, this is equal to plus and minus square root of 33 over 7. So 33 over 7. Okay? So what does this mean? What does this mean? Your solutions will be x equals negative 1 over 7, y equals positive square root of 33 over 7, z equals 10 over 7, and x equals negative 1 over 7, y equals negative square root of 33 over 7, z equals 10 over 7. Meaning, you have two sets of solutions. Okay? So therefore, thus, the solutions are So let me adjust this again. So the solutions are you have negative 1 over 7 square root of 33 over 7 10 over 7. And then the other, it's negative 1 over 7, comma, negative square root of 33 over 7, 10 over 7. So these are the two solutions. Okay? Questions. Questions? So, we're done with those two examples. Actually, not exactly these two examples. What we did earlier was this, but we don't have the squared part. Okay? But you can also do the one with the squared part and then just do the other examples. Okay? So again, that's the last example. Okay? And for you, you can work on the other examples that we have here. And in here, in the last example, there were no z squareds, but originally what's written here, there were squared. So you can also work on this. Okay? So thank you and hope you've learned uh, something. Bye bye.